Life is divided into species, but how many species are there? It was over 250 years ago that Swedish biologist Carl Linnaeus, a man of short stature but imbued with a grand mission and an ego to match, set out to classify all of God's creation. He decided that, in all likelihood, there are only 10,000 species of plants on our planet. Our current estimate for flowering plants alone is about 400,000 known species. It is estimated that we have only described around 1.2 to 1.5 million of all the species on our planet. Just how many species are there in total? Now, this is an important question, a question that goes beyond simple bean counting, as knowing the total number of species and their ecological roles and relationships may have serious implications for how we estimate what the minimum number of species may be needed to maintain a healthy biosphere. Estimates of the total number of species on Earth have varied wildly between 3 million and 100 million, depending what you are counting, on how the number of unknown species was calculated. One approach, taken by Camilo Moura of the University of Hawaii and fellow researchers at Dalhousie University in Nova Scotia, may help bring that number into a little more focus. Their estimates only consider eukaryotic organisms, those single-celled or multicellular organisms that are more complex than a prokaryote like a bacterium. That is, everything from a paramecium to a penguin. They considered the taxonomic arrangement of species to make an estimate. They looked at the way that species are ordered into various hierarchical groupings and suggested that there is a consistent numerical trend in the number of species in each level of this hierarchy. They validated their hypothesis by testing it against well-known groups of taxa and came up with an estimate of around 8.7 plus or minus 1.3 million species on Earth. If this is the case, it would mean that around 86% of land species and 91% of marine species may remain undescribed. Other studies are more conservative, however, placing the number around 3 to 5 million species in total. But importantly, both estimates are comparatively close, within a factor of about 2. Whatever the total number of species, the diversity of life on our planet is staggering. But how long have we had this situation? Well, although we have likely had life on planet Earth for around 4 billion years, the spectacular biosphere we see all around us today may be relatively new, possibly representing as little as 13% of the total history of the biosphere. For most of Earth's history, life was simple and single-celled. It could pull off some pretty amazing tricks like photosynthesis, and by 1.2 billion years ago, we do have evidence of some of the first multicellular algae. By 542 million years ago, skeletonized invertebrates have made an appearance, but to be honest, most of the creatures during the first 3.5 billion years of life story would not make a particularly awe-inspiring zoo exhibit. Nothing quite like what Richard Dawkins rightfully calls the greatest show on Earth. So in this episode, let's look at how we get the first indications of a diverse biosphere and ask, what was Darwin's dilemma? What are the first stirrings of an enlarged biosphere? How would these new organisms develop? And why did this first Big Bang of life occur, and what happened to it? Charles Darwin's theory of evolution by natural selection elegantly accounts for all the wonderful diversity we see all around us today. His theory predicts that through time there should be a lineage of creatures eventually ending with what we call today Luca, the last universal common ancestor. As he stated, therefore, I should infer from analogy that probably all the organic beings which have ever lived on this earth have descended from some one primordial form into which life was first breathed. Darwin was well aware that fossils were useful indicators of past life in ecosystems, but also understood that the record was incomplete, stating that it had only here and there a short chapter preserved. Even so, the fossil record should still demonstrate increasing complexity, from simple forms following the distant early Precambrian dawn of Luca to the more complex biosphere we have today. There was a problem though, because close to the base of the Cambrian period, today dated around 542 million years ago, the fossil record appears to indicate that a diverse array of large, complex creatures apparently materialised out of thin air. This appearance occurred even though life appeared to follow Darwin's predictions after the Cambrian period. This emergence of a complex biosphere geologically in an instant was contrary to what Darwin had predicted. Darwin himself suggested that as paleontology exploration continued, simpler fossil forms would likely turn up in older strata, but for a while this was a problem. Today we are aware that Darwin's dilemma is related in part to the fact that the pace of evolution did not follow the traditional slow, steady-state views of the theory that many held at the time. Indeed, complex life and all the major plant and animal phyla that we do know today did appear in the record rapidly. Essentially, the large biomineralized arthropods such as trilobites that we find around 521 million years ago, just 20 million years into the Cambrian period, arose geologically in a few short breaths. Today, this rapid evolution of large animals is called the Cambrian explosion and has been covered in detail in books, in magazines and on television. Our insights into the world's biosphere just following this explosion of life were greatly expanded by the discovery of an extremely important fossil treasure, the Burgess Shale deposit in British Columbia, Canada, by one of the Smithsonian's most famous secretaries and director of the National Museum of Natural History, Charles Walcott. The discoveries of Walcott and later discoveries of Burgess-type deposits span the early and middle Cambrian, with the oldest being found in China, dating to about 550 million years ago. Together, the Burgess-type faunas paint a picture of a wonderfully diverse biosphere, with the majority of the major phyla represented. But was this the only big boom for complex life? Is it possible that there was an earlier explosion of life, a precursor to the explosion so wonderfully represented in the Burgess Shale? To answer that, we stay in Canada, but this time travel to the other side of the country, to the beautiful province of Newfoundland. Newfoundland lies off the coast of eastern Canada in the Atlantic Ocean and has a long and fascinating geological history. It was on Newfoundland that the birth and death of an ancient ocean called Iapetus is recorded that we covered in an earlier lecture. Newfoundland also has a long history of habitation of indigenous peoples and also Vikings, but it would start to become more well known to Europeans when explorer John Cabot sailed into the area in 1497. Cabot was particularly startled by the richness of the fish around its shores. John Cabot's crew reported, "The sea there is full of fish that can be taken not only with nets, but with fishing baskets." The fish stocks, now unfortunately much depleted in Newfoundland, were in part one of the great draws to the area. Ships had to be careful though. In the foggy and rainy conditions, very common in those parts, a ship heading towards Cape Race could turn north prematurely and hit these unforgiving rocks. This is why the area is called Mistaken Point, a site of many shipwrecks over the years. But these rocks tell another story. This story, though, would have to wait till 1968, when a young graduate student from a very different part of the world moved to Memorial University at St. John's, the capital city of Newfoundland, to start his master's degree in geology. Shiva Balat Misra was born in a small village near Lucknow in India. As a boy, he had to walk over 15 miles to go to school each day. After winning a scholarship to study in Canada, he arrived in a very different world to his native India. Little did he know that he would also ultimately discover an entirely lost world as well. He was tasked with completing a geological survey of the area that includes Mistaken Point and the production of a geological map of the area shown here. What the young geologist would discover was amazing. Now, if you're lucky enough to receive a permit to visit Mistaken Point, you will find a series of gently dipping rocks like giant steps across the landscape. If you take a look on the surface of those rocks, particularly if the sun is low on the horizon and casting high contrast shadows, an entire ancient world is revealed. Preserved in these rocks is an extensive ecosystem, many believe to be complete, incorporating all of the life forms that were present at that time, what we call a biosynosis or life assemblage. What Mizra revealed was an ancient deep ocean floor, complete with the creatures that were living on it. The rocks are now mudstone, but were originally muddy sediments. The creatures he found living in these deep water, low oxygen conditions are from the latest Precambrian on what is now the Avalon Peninsula. At the time, this area was located between 40 to 65 degrees south latitude, very different to its current location at 46.6 degrees north. The quiet, low oxygen conditions these creatures lived in probably aided in their preservation, but another important feature is their location, close to an ancient volcano. Of course, the volcano has long since been eroded away, but the ash that it spewed settled down through the water column, burying the creatures where they lived, like an ancient version of Pompeii. The ash helped cast the fossils by forming an external mould, but it helped in another way too, by providing an absolute date for the entombing sediments by radiometric dating. We covered this in an earlier lecture, but let's review the basic principles again. Volcanic ash contains crystals that start to form in the magma chamber of a volcano. As that magma fragments in an eruption and is violently ejected as ash, some of those crystals are incorporated in the ejector cloud. Many crystals, particularly zircons, contain small amounts of radioactive material. Once zircon crystals are formed, the radioactive components start to decay, yielding stable, non-radioactive daughter products. As the decay rate is known from laboratory experiments, the ratio between parent to daughter material acts a bit like a ticking clock, used to date the sediments entombing these fossils. From this, we know that the fossils at Mistaken Point are about 565 million years old, in a period we call the Ediacaran. The creatures you find here are not like any we see today. Many of these fossils are collectively called rangiomorphs, frond-like creatures that are composed of single budding elements that divide and repeat over 4 levels of organisation in a simple fractal-like manner. This simple type of reproduction is a simple yet effective solution to build large bodies from small, self-repeating elements, a bit like toy bricks. To build a body like this, you would probably only need about 7 or 8 genetic commands. For comparison, we consist of over 25,000. Although these creatures were fixed in one location, they should not be mistaken for plants or seaweed. They were something very different. These and related Ediacaran organisms don't have a mouth or a gut, and some have suggested that they were osmotrophs, absorbing nutrients and organic material directly from the seawater through their bodies. Their simple, fractal, self-repeating body plans help them increase their surface area for absorption of material from the surroundings. They were certainly not photosynthetic, as they lived well below the photic zone, the depth to which light can penetrate into water. Reproductive organs appear to be missing too. Perhaps they just budded or released one of their cactus-like reproductive elements into the ocean that would sink to the ocean floor and start to germinate, thus growing another fractal-like creature elsewhere on the bottom of the ocean. It is very difficult to find anything currently living that looks anything like these very strange creatures. Many suggestions have been made, ranging from obscure groups of primitive invertebrates to groups of very large protists. Guy Narbonne of Queen's University have suggested they might represent the primitive ancestors of a large modern group of creatures, perhaps animals or even fungi. Or perhaps, as suggested by researchers like Dolf Seilacker, they represent a completely separate and distinct group of life, the Vendozoa, that flourished during the Ediacaran but didn't make it into the next Eon, the Phanerozoic. The most common type of rangiomorph found here are spindle creatures like Fractofusa mizrae, named in honour of Professor Mizra. The largest of these creatures were about a foot long and found on the ocean floor, From either side of a central rib was a series of subordinate ribs that were further subdivided into fronds in a typical rangiomorph manner. Some of these organisms were more elevated and upstanding. This is Bradgetia, a brushy kind of cabbage-looking like creature that sat on the ocean floor. Large specimens of this species stood about 8.5 inches, that's 21.5 centimetres tall. Occupying higher levels of the water column, swaying in the water like modern kelp, were creatures such as Charnia, long and ribbon-like and about as thin as your fingernail. Some reaching lengths of about 6.5 feet in length, although most were pretty much smaller, possibly reflecting the increased scarcity of nutrients away from the sediment-water interface. So this is the picture of life, the first attempt that life really had to get big. Thin creatures with no mouths or guts, simple building block-like creatures fixed onto the substrate in darkness. Collectively, this ecosystem from Newfoundland is known as the Avalon assemblage, and this initial burst of large creatures has been termed the Avalon explosion. But this is not the only assemblage of creatures known from the Ediacaran period. There are two others that are found in different environments, the White Sea and the Nama assemblage. Both of these biotas should also be considered, for they have an important story to tell too. The first of these, the White Sea assemblage, was named for a typical occurrence of the assemblage found in northwestern Russia. The Russian assemblage, though, was not the first group of these particular Ediacaran creatures to be found. The first discovery of these creatures came from the Flinders Range of Australia in the area called the Ediacara Hills. In fact, it is this area that lends its name to the latest interval of the Precambrian, the Ediacaran period. Like the Mistaken Point fossils, these too were a surprise and discovered by a young geologist, one Reginald Sprigg, who had been sent to this area by the South Australian government to see if some old mines in the area should be reopened. The story goes that he was eating lunch when he observed the impressions of fossils on a rock surface. The fossils are dated at around 550 million years ago, younger than those from Mistaken Point in Newfoundland. The environment that the White Sea creatures lived in was very different from those discovered in Newfoundland. The White Sea fossils lived on shallow, sandy sediments in sunlit waters in temperate conditions. Storm events would occasionally smother entire communities and preserve them more or less intact. The third assemblage type, the Nama assemblage, consists of forms that are interpreted as being more tropical in their distribution. They've been recovered from sections in Namibia, southern Africa. The temporal relationships between each of the assemblages is disputed by some, but in general the Avalon-type cluster of species appears to be the first pulse of innovation, followed by a second wave represented by the White Sea and Nama cluster of species. The second wave Ediacaran creatures still contain the frond-like rangiomorphs that we see in Newfoundland, like Charnia, a sample of which from the Ediacara Hills in Australia can be seen in the National Museum of Natural History. It is possible that the Avalon-type assemblages still existed in the deep, dark waters surrounding the continents, but in the second wave there were other new creatures too. There are triradially arranged organisms like Tribrachidium and pentaradial forms like Arcarua, suggested by some to be ancestors of echinoderms, from which we may get urchins and starfish, although this link is somewhat tenuous. Something else has evolved though, strange-looking creatures like Dickinsonia. Dickinsonia is an animal that looks like a large segmented flatworm and could range in size from a penny to several feet in length. What it actually is though is still very much in dispute. It is possible in Dickinsonia, though, that we find evidence for a low-energy type of mobility in the biosphere. The floors of the oceans in these shallow marine environments were encrusted with microbial mats, some of which have Dickinsonia-shaped impressions, perhaps suggesting that it was adopting a strategy of absorbing the microbes in a particular area of the mat, and after a feeding event, picking up its skirts and then moving on to another location. Of course, this doesn't prove that Dickinsonia was moving under its own steam, but it does show that not all large creatures were fixed to the substrate. And consider Spriggenia. a creature that appears to have a segmented body specialised into definite functional areas, the possibility of a head and a tail as well. Was this a creature that was going places and probing the sediment or its surface for food? Sprigina has been touted as a possible forerunner of the arthropods, and it does look a little like some of the trilobites that would be a common component of the Cambrian period. We will look more closely at this in another lecture. But if you want more convincing evidence that the biosphere was starting to move around, you should consider Kimberella, a slug-like creature that could reach lengths of about 6 inches. Kimberella shows definite signs that it was interacting with the sediment, probably feeding on microbes on the sediment-water interface. Scratches on the sediment may represent feeding marks left as Kimberella raked the surface for microbes. This is evidence that the biosphere is no longer passive. It is actively interacting with the rest of the Earth system. Kimberella is significant for another reason too. It is bilaterally symmetrical and consequently represents one of the earliest fossils of the most species-rich group of animals, the Bilateria. The Bilateria is a major group of animals that excludes sponges and corals. Some have suggested an even more refined relationship, suggesting that Kimberella might be an ancestral mollusk, an ancestor of calamari and escargot everywhere. So, if you were snorkeling, preferably in one of the more tropical Ediacaran locations, you may have seen a biosphere that was no longer static, a biosphere beginning to show glimpses of the wonderful animals that were to follow. Animals with a definite front and a definite back end, animals that would differentiate the bodies to form specialised functions, animals that would move and interact with their environment in a variety of diverse and wonderful ways. But why did this event occur at this point in time? What was driving the Avalon explosion? Around 2.5 to 1.85 billion years ago, it is believed that the photosynthetic bacteria had started to deliver significant quantities of oxygen to the surface sediments, oceans and atmosphere of the Earth system. Following that interval, the Earth enters into a period called the boring billion, between about 1.85 and about 1 billion years ago, where nothing much appears to change in the Earth's geochemical or biological systems. Things would change though, with a series of global glaciations called snowballs between 850 to 635 million years ago, within a period called the Cryogenian, that were probably related to the breakup of a supercontinent called Rodinia about 850 million years ago. A possible explanation may be related to increased weathering rates following the ends of a snowball event. This would fertilise the oceans and cause a bloom of photosynthetic microplankton and a release of atmospheric oxygen. The increased erosion rate and delivery of sediment to the ocean would also increase the rate at which organic material was being buried. This would remove the organic material and reduce the amount of oxygen that would usually be used up in its oxidation, further contributing to the buildup of free oxygen. Following the snowballs, oxygen levels would have increased to such a level that it would be possible for creatures composed of multiple cells to exist. Prior to this, oxygen concentrations were only sufficient to power a microbial level of biological organisation. This would allow larger creatures to evolve as oxygen could now diffuse through layers of cells. It has also been suggested that a more oxygenated ocean system would also make available trace elements that would be key in the development of more complex metabolisms. Well, at least that's one hypothesis. To be honest, the story of oxygen in the Earth system is a complex one and changing very rapidly. It would appear that oxygen levels fluctuated dramatically through the Ediacaran period and into the Cambrian period. Some researchers, like Doug Irwin of the Department of Paleobiology at the Smithsonian, have suggested that the actual roots of current diversity may lie even earlier than we thought, perhaps within the Cryogenian period, the age of the great snowballs. He suggests that the snowball of the events themselves may have been a kind of proving ground where many animals developed their genetic toolkits, priming the fuse for the diversification of the Avalon and Cambrian explosions. But what happened to the Ediacarans? At the end of the Ediacaran period, there is a large shift in carbon isotopes recorded in the geological record. With each of the 5 mass extinctions, starting with the extinction at the end of the Ordovician about 443 million years ago, a similar perturbation is recorded and often relates to a severe disruption in the biosphere. So does the Ediacaran biota disappear because of an extinction event caused by some maybe unknown perturbations in global geochemical cycles? Or is it possible that their removal from the fossil record may simply be a result of changing conditions of preservation? Many Ediacaran organisms are partly preserved as a result of microbial mantling, a mask of microbes that grew over dead Ediacarans and aided in their preservation. With the advent of more sophisticated grazing and burrowing animals, the unique conditions that preserved these creatures ended, and with it, the record of the Ediacarans too. But there is another possibility, one that invokes a replacement of Ediacarans by other animals. In addition to his interest in the Ediacaran biota, Doug Irwin has made many contributions to our understandings of mass extinction events. In 2015, he and a number of his colleagues from various universities in the United States released a paper exploring the possibility that the disappearance of the Ediacarans represents the first mass extinction event. I must admit that in general, I've always regarded geophysical causes like volcanic activity, glaciations or meteor strikes as generally the triggers of mass extinction events. What Doug Irwin's paper proposes, though, is that life itself may have caused a crisis for the Ediacarans. As we have already seen, the early Ediacaran animals, although a fantastic leap forward in complexity, were essentially immobile, probably passively absorbing nutrients from seawater. By the time we see complex animals, things have started to change. The biosphere is starting to actively interact with the rest of the Earth system. Animals have become ecosystem engineers. Is it possible that these new bioengineers change conditions so much that it make life untenable for the Ediacarans? Doug and his colleagues examined some of the youngest Ediacaran assemblages from locations in Namibia called Farm Swartpunt. They hypothesized that if this biotic replacement model was correct, then the extinction mechanism there should have 2 effects. Firstly, there should be an increase in the size and variety of trace fossils left behind by increasingly complex animals interacting with the ocean sediments. And secondly, that the younger Ediacaran assemblages should be relatively depauperate, that means reduced in species, when compared to older assemblages like those in Canada, Russia and South Australia. The presence of relatively high diversity trace fossils in many sections of uppermost Ediacaran and lowermost Cambrian rocks, including those at Farm Swartpunt, supports the idea of increased ecosystem engineering at this time. They also noted a drop in diversity of the Ediacarans at Farm Swartpunt. Obviously, this is still only one location, and it was located at relatively high latitudes at time of deposition, but even so, diversity was much lower than was expected, and there is no evidence of environmental stress to account for it. What is suggested is an Ediacaran assemblage that was becoming increasingly outcompeted and marginalised by developing Cambrian fauna. In physically interacting with the oceanic substrate, these new Cambrian forms would have competed for resources, increased the delivery of carbon to the ocean floor, and more effectively mixed and oxygenated ocean sediments. For the Ediacarans, the world was changing beyond their ability to adapt, and they faded away, leaving the stage set for the Cambrian explosion. Whatever their fate, by the time we see the first large fauna of the Cambrian, the Ediacarans, like the rangeomorphs and similar creatures, are gone, either suddenly or gradually, replaced by other creatures. The putative ancestors of later organisms, such as Kimberella, are gone too, their ancestors evolving into the wonderful creatures from the Cambrian explosion, thus laying the foundations for the greatest show on Earth.